Hi, everyone. I want to take a moment just to thank you all for being here today to listen to our September Beaver Speaker Science Series presentation. My name is Lauren Taylor, and I'm the Policy and Science Director here with the Beaver Institute. And I'm really excited to introduce this month's speaker, my colleague Jordan Kennedy. And just to give you a little bit of background on Jordan, Dr. Jordan Kennedy is an interdisciplinary researcher and engineer whose work bridges non human animal engineering, hydrodynamics, and indigenous-led conservation. As Tribal Partnerships Liaison and Beaver Behaviorist at the Beaver Institute, she integrates traditional ecological knowledge into conservation, policy, and management while centering Indigenous sovereignty, ethical research, and data governance. Holding a Ph.D. and master's in material science and mechanical engineering from Harvard University, her research spans beaver damming behaviors, logjam hydrodynamics, biomimetic design, and beaver-inspired robotics. She is a postdoctoral researcher at Harvard's Graduate School of Design, developing distributed robotic platforms for landscape architecture, and a research fellow at Outer Coast College, creating curricula that unites engineering, physics, and indigenous epistemologies. Jordan, I'm so excited to hear you talk today, and with that, I will turn it over to you.
And just confirm for me you can see it. And good?
We can see it. You are good to go, Jordan. Thank you.
All right, thank you. I'm a bit frazzled because I ran in from my kid's bus, so just let me take a minute to breathe. And I'm going to talk about beaver-inspired landscape design, and I'm going to be framing this as a very much a process-driven design. Is it the next slide's up? So Lauren, thank you so much for introducing me, but Oki. My name is Jordan Kennedy. I am currently a postdoctoral research fellow at the Graduate School of Design at Harvard University, specifically in the Department of Landscape Architecture. And I have a very strange background. I'm a mechanical engineer by education and training. And I've been, during my PhD, I specialized in how non-human animals build, and with a particular focus on the North American beaver. And what came out of that was a lot of insights into beaver behavior. And I've been applying that framework of beaver behavior currently to multi-agent robotic systems for applications in landscape design. I am also the Tribal Partnerships Liaison and Beaver Behaviorist for the Beaver Institute. Yay, thank you. I'm a descendant of the Blackfeet tribe. I grew up on the Blackfeet Indian Reservation. And so when I think about working with other species, there is a real sense of kin empathy, being deeply inspired by and trying to understand how animals think and interact with the landscape. And I also like to think of myself as a bit of a beaver futurist. I give that to myself, but I'm also the co-PI on the NSF with Emily Fairfax and Jonah and Sandra, which her name's not on there. Oh no, I thought it was on there. And I've currently been integrating traditional ecologic knowledge and tribal narratives through culture and media and storytelling. And I'm from the Great Plains. So that's where my knowledge base is. These are some of the collaborators I'm working on with this project, this multi-agent robotic systems project for landscape design, a very multidisciplinary topic, requires a big team of people from all over the world. I have my PI, Karen Lee Bar-Sinai. She's a landscape architect. I have a team of engineers out of Israel who specialize in landscape robotics and also programming multi-agent systems. I'm working with landscape architects, specifically with William Bowles, where he specializes in how to uh, integrate human interaction with landscapes to inform design. I also work with Justin Werfel. He's a roboticist and a computer scientist. I work with Nathan Mellibrick. He is an engineer and an architect. I'm working also with two undergrads, both one in mechanical engineering, another in computer science, who are all working on different aspects of this project I'm going to be presenting on today. And then, of course, the Beaver Institute for helping me ground my work and doing everything I can to make this work relevant and meaningful in the context of what it is to work with beaver and alongside beavers and promote beaver coexistence on the landscape. So let's talk about designing across ecosystems. Why do we even want to think about beavers? So beavers are spread across North America and Europe. And one of the key things about beavers is they're able to live in a variety of different habitat types because they're able to modify those habitats to meet their life cycle needs. And they live in colonies of anywhere from 2 to 10 individuals. And they are the largest rodent in North America, and they are very social. So let's talk about beaver constructs. So I have two categories. I have the multi-generational, hand wavy. So beaver famously, so dam slow velocity and deep in the stream, but they don't just build the dam, they also excavate the canal directly upstream of the dam. So the pond isn't just flooded, it's actively excavated as well. So it's an engineered feature. Beavers also excavate canal systems for material transport and foraging. And then they have structures that don't persist as long on the landscape. They have lodges, which they live in for 1 to 2 years. They also build extensive trail networks in order to access materials. They have their food caches, and then they have their scent mounds. And all 7 of these architectural constructs come together to build the beaver damming complex. And the beaver damming complex is many times larger than an individual beaver and can consist of many of these architectural constructs as big of as part of the much bigger architectural complex. So you can have multiple dams, multiple ponds, extensive trail and canal systems. Oftentimes you can have multiple lodges. And these beaver damming complexes are multi-generational by nature. So this is a satellite imagery from 2003 to 2014, and then 2017 is a drone-generated map of mine of the exposed water of this beaver habitat in the prairie landscape. And I think two things that are notable about these pictures in time, is there wasn't any water until the beavers moved in. So this is a groundwater system, and they were able to excavate it up to bring water to the surface, but also to the time that it took for these systems to build. So these damming complexes, in addition to being much, much larger than any individual beaver, also take generations of beavers to build, working together. But more than that, these damming complexes are bespoke to the landscape. The final structure that emerges is custom. So here I have shown 3 damming complexes, one from Alaska, one from Massachusetts, one from Argentina, all North American beaver. And I have exposed water, and this exposed water is representing the beaver ponds and the beaver canals. And one thing that happens with these systems that becomes evident just by looking at these is how diverse they are. So even though they have all of these discrete architectural elements, the final damming morphology, the final damming complex morphology is custom to the landscape that it's on. Here's some more examples of that. I have an example here at Acadia National Park. I have another one out of Colorado and another one out of Finland, where beavers are an invasive species. But the idea being that what emerges is a damming complex that can be defined by all of these architectures, but the final shape is amorphous and completely in custom to the landscape that it is on. It's also a dynamic architecture. Here I have shown a GIF of the exposed water of a damming complex from Acadia National Park. I got this in from these traces. One of my students made the traces for me, and this is taken from Google Earth satellite imagery. And one of the things that you can see is the evolution of these canal systems over time. So beavers don't just build once. They're constantly building, they're constantly expanding, they're constantly changing these damming complexes as they're being built. This here is an overlay map from 1991 to 2023 of the same site that I just showed you on the previous slide as the GIF. And the brighter the white, the older the water is. And so over time, we can see the slow growth and expansion of these damming complexes, particularly through the canal architectures. So beavers are individual workers working across generations. And even though I've used this this image so many times. It's one of my favorites because it just illustrates my point so well. And like, it's also the longer you look at this image, the worse it gets. So this here is a drawing from a map inset in the early 1700s. And this particular inset was used as motivation to invest in the wealth of North America, where the wealth of North America came from the fur. And the beavers were one of these big drivers. And so there's a political motivation to this photo, but one of the things that I like most about it is there's around 50 beavers in this image, and they are all distributing their work in a very Henry Ford-esque style. You got some beavers moving some logs on their tails. You got some beavers on a different station clearing, like, taking the bark off of sticks. You got a few more beavers taking down trees. And you got to, even if you're skiing ramps, like one of the things that I like about this, in addition to it being just hilariously wrong, it serves as a really good foil for some of my conclusions on how I think beavers build. So hypothesis one, as first shown by this picture here, is that beavers build in a coordinated and organized way with a division of labor. And this is the way I think humans like to build. And Henry Ford made a fortune, designing cars to be built in stations. And I really like this concept. And then another hypothesis around what drives beavers to build and how they're able to coordinate this building behavior. And this is actually quite a famous hypothesis, that the sound of running water triggers beavers to build dams. Well, seems to be anecdotally reinforced throughout the literature. I've only found 2 studies on it, and neither of them produced data that was statistically compelling. But there does seem to be a bit of weight to this sentiment. But within any ecosystem that has running water, the louder the water, the more beavers build. At some point that fails. Otherwise, beavers would be trying to build dams across waterfalls like Niagara Falls in the background of this photo. And trying to build in these areas would never persist. The shear is too high. So at scale, this argument starts to get a bit cartoonish. There was some various things that came out of this work. One, that dam building and behaviors is innate. So this was observed that beavers have a genetic predisposition to build. And this was seen in the kits that would engage in building behavior without being taught to do so. And then another thing, there's this like famous adage, as busy as a beaver. Well, not really. So given the opportunity, beavers are going to move into areas where they do not have to engage in building behaviors. So building, therefore, is a response to suboptimal hydrodynamic conditions. So the first construct. So when we think about beavers, I think the idea that comes to mind first about beavers is that they build dams. And so during my PhD studies, I was interested in how beavers are able to build dams. And one of the features that I saw appear on the landscape before anything was ever built was the beaver trail. And I didn't really understand them when I first saw them. But when I went back and I plotted this data, I found that trail building always precedes dam building. And that the beavers, in addition to building these trail systems, expand on these trail systems throughout the season. So this here is a dam complex consisting of 4 dams that are in the bright white. And then I have the stream here. And then I have the trails. And on these trails, you can see over time the expansion of these systems, where the lighter the trail, the older it is, and the newest trails are of this darkest shaded gray, and they expand over the season. And one thing that's notable about this is that beavers are frequently following the trails and expanding off of them and branching off these trails. So when I first started my PhD work, I was really captured by this idea that flow triggers beavers to engage in dam building behavior. But the more I looked at my data, I couldn't ever really see that. I couldn't see anything in the data that indicated that dams themselves were directly correlated with flow, at least when it came to behavior. But what I did see that fell out of my thesis work was that trail building was initiated over a very small range of flow rates. And so flow being a massive or being a considerable environmental influence for when beavers start to engage in construction behaviors. And so these trail systems are the first structures to be built, which makes sense because it enables beavers to find their bills to build the dams in the first place. A trail system has to be established first, but also these trail systems, when they are built, are established over a relatively small range of flow rates, indicating that the beavers are very much responding to the conditions of the environment to know when to start engaging in construction behaviors, including trail clearing and dam building. And then the other architecture I want to put your focus on is the canal. And I view these canals a bit as long-term memory. So you got to see a bit of the canals in the previous slide through the exposed water. And so what I have over on the right-hand side of the screen is a canal systems from 1990 to 2022, where the darker the color, the older the canal, and the lighter the color, the newer the canal. And one thing that was notable about this particular system is that it expanded and it contracted, and it expanded and it contracted, but on the whole, it continued to grow outward over time. So from 1990 to 2022, what was once a simple stream that didn't have very many connections became a vastly interconnected dynamic wetland through the continued occupation of beaver and their excavation of canals. And so as part of my thesis work, all of my thesis hypotheses to begin with were all about dams, and I didn't find anything. So from dams to trails and canals, the one thing that I was able to find is that beavers preferentially start new trail systems where canal systems have already been established. So from that, hypothesis being that trail and canals are decentralized coordination mechanisms for beavers. So if a trail system is productive, that means if a beaver has initiated a trail and they're able to successfully harvest vegetation or find another aquatic resource like the other side of the river or a pond on these trails, they begin to reinforce these trails into canals through repeated usage. And so these trail systems are functionally short-term memory for the colony, but over many, many generations of repeated use are embedded long-term memory into the landscape that other colonies of beavers can tap into to know if this site is a good candidate site for recolonization. So the way I think about beavers is they have constant conversation. I think that when I think about beavers and I think about design, particularly as we're thinking about how can we learn from beavers in sustainable design of our landscapes, is I think about beavers as being in constant conversation with the landscape. So but also beavers across time. So their beavers aren't just speaking to their own colony members. They're able to do this short-term conversation through the trails, which are cleared and then grown over every single season. But they're also able to engage in long-term conversation to other beaver colonies across generations through the excavation of canal systems, which persists for a very long time on the environment. And then the beaver is also in conversation with the environment. And with my thesis studies, the primary inputs seem to be flow for when to build, vegetation, habitat quality. A beaver cannot colonize a site unless there is sufficient enough materials for them to survive. And then water quality. Although that didn't necessarily fall out of my thesis work, it's pretty obvious as we're looking at these overly degraded sites and thinking about ways to get beavers back into them, how important water quality is. And then there are secondary inputs like any prey species has. So one of the paradigms for thinking about designing like beaver is to think about architecture as a form of language. So if we can learn from beavers on how to speak with landscapes, perhaps we can too. Perhaps we can learn to design landscapes in a way that is with care as opposed to prescribing some design on the landscape. Rather, we are going to be able to design with the landscape instead against it. So can we learn this language of architecture through the studying of beavers? So beavers don't just exist in a single colony, like they are complex critters and they exist on multiple scales, and the architecture we're seeking to emulate also emerges on multiple scales. So it's important to understand how the individual behaviors of beaver over time give rise to the spatial and temporal complexity of these landscapes that are so beneficial to the ecosystem. But in addition to that, how can these landscape modifications, so the architectures that beavers leave behind via trails and canals, be useful in informing future generations of beavers, the potential quality of that side? The beavers have their daily activity, the foraging, the harvesting, the building, the sleeping, but all of this is dictated by seasonal. So in the winter, they're usually in their lodge under the ice. In the spring, they're dispersing new sites, and so they're very heavily invested in construction activities if their site does not meet their life cycle needs. If they moved into a pond, they might not build at all that summer. So good for them in that beaver colony. And in the fall, everybody has to build, especially in northern regions, because you have to food cache. But then all of this is on the colony cycle. This is happening over many years where beavers will move into a site, they'll colonize it, they'll raise their kits. That site becomes depleted as they take out the vegetation. But while they were there taking out the vegetation, they were building their trails, they were building their canals, and their canals were expanding the riparian zone. So over time, that area becomes even more amenable to the vegetation that they love. And so then the vegetation's back in, and then another colony will move in because the vegetation is good, or perhaps the same colony will move in and they'll raise kits there and the resources, and then they will move out when they are gone, and the site will start to regrow again. But this time it's wider and bigger because the beavers made even more connections through their canal building, their dam building. They fundamentally changed the hydraulic, and as a result, the trophic cascades made it so ecologically beneficial that basically they're farming over the multiple generations. Beaver is in a habitat, the more amenable that habitat will be over the long term. And so to test some of our ideas about this, right? So like what I'm throwing out of the way is a lot of hypotheses. This is what I think beavers are doing. I think they're communicating across space-time using architecture as a medium. I think that they're that they're working in these multi-generational cycles and that they're able to communicate across colonies and coordinate across colonies through, the distributed embedding of architecture in the landscape. Even as dams fail and trails grow over, these canal systems persist from one generation to the next. And so to test these hypotheses that I am throwing at you, we are building a multi-agent simulation to test the behavior of beavers as we assume them to be, but also at the interface of the dynamics of landscapes, because landscapes have seasonality. They have low flow, high flow, fire, disaster. There's variability in materials, there's variation in flow. And then the beavers themselves, interacting with landscapes that are highly variable, different types of vegetation, density, types, flow conditions. The behaviors, how do they follow these trails? How do they follow these canals and ramify them, keep excavating on them? And then, of course, they're living in a real environment. So what are the physical limitations of real landscapes, including things like gravity and slope and obstacles that are immovable? So this particular question, and I'm partnering with Federico Olivia. He is a postdoctoral research in Israel, and he specializes in multi-agent robotics, and he works in the Civil, Environmental, and Agricultural Robotics Lab. And he has been helping me design this framework based on my years of knowledge about beaver to build this multi-agent digital system. And so the goal is to have realistic digital beavers engaging in harvesting and all the different things that arrive from that, and also having a realistic simulator that can capture the dynamics of these environments that we're testing them in. So this here is a beaver trail, and notable to this is all the branching. And but also noticeable to this is a prairie system and there are no woody vegetation here. But if you compare this to a region where trails are being built and there is a considerable amount of woody vegetation, in this case, it's Asher willow, these trail morphologies take on a different shape. They harden, they're less branchy, and there's less branches falling off of them, and the primary stems are much, much longer. So there does seem to be a behavioral difference between how once beavers are navigating an environment looking for food versus when they find it, and how they're able to move that back and then reinforce that trail into a canal. And you can see even at the end of this trail system, they're already starting to turn that into a canal. And so this is, just, some speak about what the beaver is seeing within their environment. How are we thinking about how they program, how they move, how do they see? And one of the questions is ranges. So there's D4, which you can see backwards, forward, left, and right. There's D8, which you can see are diagonals. D24 gives you some range, and D40 gives you even more range. But we realize in these environments, it's complex. There's trees, there's all sorts of things blocking your view. And so these slope gradients are incredibly important, which we have in this red box I have shown, in order to figure out how beavers are able to navigate around obstacles. Because functionally, even though they're building these massive ecosystems, they're not very big. They can't see the whole thing. So they're making local decisions, and it's giving rise to this incredible complexity. And it would be nice to understand, how are they making these local decisions? And we're testing our hypotheses with the simulator. This is the local map. So as the beavers are going along, every time they're moving around in the landscape, they're actually building their own internal map of the landscape, and then they're leaving the that information behind for other beavers through the formation of canals, or a trail. So if a beaver knows that a trail is here, that's to say, oh, another beaver has been here before. I already know that it is mapped. I already know that this is a spot. And then the environment itself, instead of modeling vegetation as discrete points, we model vegetation as a gradient of quality, where you have areas that have very high quality vegetation and areas with very low quality vegetation. And if you're a beaver, you want to not necessarily optimize, but find a happy middle ground between how far you have to move to get that really high quality vegetation, but also and have to move it back, right? Because you still want the good stuff. And right now we're in the hypothesis testing phase. I am showing you ongoing work. This is not polished and ready work, but these are some of the things we're thinking about on as these agents are navigating these digital landscapes. How are they making decisions? What's the time frame over which these networks emerge? Yeah, and this is one of our many examples that we've been testing different hypotheses on and building up these frameworks to think how beaver are interacting and exploring their environment. But that's only so useful for landscape design. So we want to hypothesis test this in reality. So we want to take these sandbox landscapes, as I showed you before, which are very critical, by the way, in the development of this multi-agent simulation, to test hypotheses, to think about movement, to think about behavior, and use digital representations of real landscapes and deploying these digital beaver agents onto them. So when I say a digital representation of a landscape, I'm talking about digital twins. So this is representing real landscapes virtually. This video that I have shown right here is a drone generated scan that I did again during my thesis work when I was studying how beavers built. I made this map using photogrammetry techniques, but I mean, there's other ways to get digital twins. So you can get LiDAR imagery that is typically available through data repositories hosted by different agencies, NOAA being my favorite. But you could go out and scan any environment you want. Or you can take scans of these real environments and modify them digitally. You can say things like, what would happen if I put a tree here? What would happen if I put a canal here? How can I modify this environment in such a way that I can potentially engage with beavers to colonize the site in the future? So there's a path divergence here, and just, for sake of time, I don't want to like go down every aisle, but this simulation at its essence is a research project to test beaver behavior in these digital environments, which allows us to do the computation really quickly. And then the other bit of it, which is the work I'm currently engaged in now, is the very much applied thinking about landscape design. It is trying to reimagine landscapes as if they had been occupied by beavers on a time scale of weeks, months, years, into decades, even to centuries, in order to help us decide on design interventions in landscapes that are too degraded. But I have my collaborators who are in the robotics field. I have me, who's very interested in behavior, and then I'm working with architects who are very interested in design. And these two slides got switched, but that's okay. So claim, the most effective way to restore habitats in North America is to partner directly with beavers, and not just directly with beavers. I think we should be partnering with bison. I think we should be partnering with prairie dogs. I think we should be partnering with alligators. But I think we, as a species, it would benefit us to identify other keystone engineers within these habitats and partner with them directly to restore habitats. However, many landscapes are too degraded and currently unfit for the colonization of many of these keystone species, including beavers. And so can the design principles that we learn from beavers, can we use them to communicate with beavers and try to get them back into these areas to co-design with them? Or, even outside of riparian zones where beavers are likely to persist, can we use these design processes and design principles to think about designing in environments where a beaver would never go, such as the desert or even, a moonscape, for instance? Can we think about the way beavers think about building as a design framework for when we are engaging with environments? So I'm going to present a case study by William Bowles. This is one of the students I'm working with. He is a master's student in landscape architecture, and he specializes in theater and landscapes and is very interested in how the human interaction with landscapes are the way you're able to make lasting change on landscapes. So right now, we are looking at a very specific site just outside of Boston called Rumney Marsh. It's a degraded intertidal zone, and it is surrounded by residential and commercial land holding. And it's also one of the areas projected to be most influenced by sea level rise. And it is currently serving as a buffer for any catastrophic flooding to the surrounding residential and commercial sites around it. And William has taken on quite the ambitious goal, building upon the work that I am doing with him. And he is looking at a multi-bodied partnership. Can we take human interventions, landscape robotics, so BeaverBot, I'll explain, and beavers in order to co-design and rehabilitate landscapes? So human interventions, planting trees, excavating canals in order to tap into the mechanism of communication for beavers to say, hey, maybe you should consider building here. Also putting plants in for phytoremediation to clean out toxin. Also putting in specialized BDAs. So this site is next to a dump, and putting beaver dam analogs in that are with materials that are capable of filtering out a lot of these chemicals would be ideal. But also because of where it is and how densely populated it is, community engagement is key in any aspect of this work because of all the investment, known or otherwise, in the design and capacity of Rumney Marsh. Now let's talk about Beaverbot. So when I say Beaverbot, I'm not talking about a single robot that can do it all. And there is this really wonderful robot being built right now in China that I think is wonderful and adorable, and I love it. I really, really love it, but that's not the type of Beaverbot I'm trying to build. So when I talk about Beaverbot, I'm talking about a suite of robotic tools to manipulate landscapes and manipulate sediments. So this multi-agent simulation that I talked about, that we are still developing and hypothesis testing against, is our framework for thinking like a beaver and informs us for how to speak to a beaver, how to communicate with a beaver. But Beaverbot is also being developed as an excavator robot to make these early incisions as canals and ponds, especially in areas that are difficult for people to reach, such as Rumney Marsh, which is a marsh, and it is difficult to navigate through it. Also having harvester robots to clear out trails, so vegetation clearing. These trail systems that beavers build are pretty critical for other species to access water when they're going down to drink. And also a deposition bot to build the more iconic dam-like structures that beavers are known for. And then, of course, beavers, and that's just letting beavers beaver. So can we restore these landscapes to the point where if we were to invite beavers back in, they would do what they do best and recolonize it and build and change it? So here is a digital elevation model of Rumney Marsh. This was taken from NOAA. And this, I'm going to zoom into our design site. And so this is the elevation of it. The black is just the water, and it's about a 70 by 70 meter plot of land. And we are going through and adding in layers of information, so design interventions. We're going through and we're making digital trees. What would happen if we plotted trees in these locations? What would happen? So X's, canals, incisions. What would happen if we put canal incisions in these locations? And then we run these through a hydrodynamic model. So this here is some of William's work on the concept of the sequence of it, where you have this initial degraded environment. On the bottom, you have hydro models. These hydro models are showing by the weight of the line how much water is moving through the system, which is also another way of thinking how much water this system can hold, which becomes very critical in these places that are very susceptible to seawater rise. And so what intervention can we make? We can start putting trees in there. We can start putting in phytoremediation plants, trying to pull out some of the toxins that are in this water system. And then as that starts to get built out, putting in these canal incisions to widen the riparian zone in the way that beavers do it, and finally get it to a point where we can reintroduce beavers back onto the landscape so that they can finish off the design by expanding the canal system, reconnecting the hydrology, and making the system capable of holding more water and making it more robust. This here is just his before and after of unoccupied beaver activity. So again, the weight of the line represents the total flow of water. That's like one of the things about working with different disciplines is we represent data differently. And so I have my beautiful heat maps and they have weighted lines that are artistically done. And so these very weighted lines here are showing you how much water should be moving through the system. So this is a before and after imagining the carrying capacity of the system. But next, we want to reintroduce the digital beavers. So this framework that I am working on with William, that I'm working on with Federico. So Federico's building the multi-agent design. William is thinking about how to design the landscape. I am thinking about beaver behavior. And altogether, we want to reintroduce digital beavers to this landscape and see how they would change it over time, and see how if we modify this design intervention or this design intervention, if they respond to it, and try to understand how beavers might interact with that landscape as we seed these landscapes with our own design interventions. This is very much ongoing work. We're building quite a big team to do this across disciplines. I talked about the deployment of these digital agents in the 3D environment, so our digital beavers, to understand how they are going to manipulate these environments over time. But also like testing these for our long-term goals. If our long-term goal is, if we design this, if we put all these interventions in and they don't produce anything, why bother? This digital framework is a way for us to test these ideas about what interventions we could put in, where to place trees, where to place canals that might inform where we want the beavers to build. Now, a beaver is going to do what a beaver is going to do, but it would be nice to coordinate with them and speaking in the way that they speak to each other. And then I have other students who are currently started on different components of the robotic build. One of my students is creating an excavator component right now, and that is going to continue to expand out. So in addition to the excavator making derm-like structures, so dam-like structures, in order to mimic some of those hydrodynamic impacts. And with that, I am done. And thank you so much for your time. And I threw a lot at you. So thank you.